Next up, we have Lauren Chambers. Are you ready?
I am. I just want to say real quick, it has been so encouraging for me to just sit here and watch all of my amazing peers give all of these presentations. And I'm sitting here trying to get nervous, but actually I'm just getting excited because you guys have just been so great. So thanks, you guys. But anyway, hello, everybody. My name is Lauren Chambers. I'm a rising senior at Yale University, and I've had the immense pleasure of working with Dr. Karin Öberg and Dr. Ilse Cleeves this summer here at the CFA. For the past 10 weeks, I've been working on a project that's actually combining theoretical physics and chemistry with computational modeling in an effort to better understand specifically how ammonia is produced and destroyed in protoplanetary disks, which are some of the earliest systems of planet formation. So protoplanetary disks are the result of, like I said, star formation. So when you have a star that is born and ignites in the center of a birth cloud, that cloud continues to collapse over time due to its own gravity and the gravity of the new star within it. And thanks to the conservation of angular momentum, that ultimately results in a disk. And the term protoplanetary comes from the fact that when you fast forward these systems a few million years, you get this. So of course, the characteristics and compositions of these planets depends really greatly on where and when they formed in the original disk. And that comes from the fact that the disks themselves are not actually uniform throughout. So as you can imagine, these disks, the gas and dust will be most dense towards the center of the disk, close to the star where gravity is strongest. In addition, the temperature will vary with respect to the amount of radiation the disk receives. So a helpful analogy I like to think about here is imagine you are at your favorite rock concert. So the star could be the stage, and of course there will be speakers right by the stage and speakers all along the sides of the venue. So it'll be loudest around the sides and near the front. If you're in the middle or if you're in the back, it might be kind of hard to hear. So if you translate sound waves to electromagnetic waves, that's what's happening kind of in the disk. And hopefully that gives you a better intuition about how the physics of this disk is actually variant throughout. But how does that relate to the chemistry and what's happening chemically here? So here are some examples of some processes that actually couple the chemistry and the physics of the disk. One is called adsorption, which is different from absorption, where a molecule actually freezes onto the surface of a dust grain. Another is desorption, where a molecule that was on a dust grain gains enough energy to sublimate or jump off the surface of the grain. Another process that occurs is dissociation, where a free photon and a free molecule interact in space, and the molecule is dissociated into its component atoms or molecules. And as you can imagine, each of these processes will happen at different rates for different physical properties. So if you have higher temperatures, you'll have more desorption and less adsorption. If you have more radiation, you can have more dissociation and more desorption, so on and so forth. But to step back for a moment, why do we actually care about chemistry in the first place? So here is a hint. Chemistry is one of the most useful tools we have for quantitatively determining whether there may be life around stars other than our own. From our extensive experience with life on Earth, we can see that life is really dominated by carbon, hydrogen, oxygen, and nitrogen, these four simple elements. And the thinking goes that if we can detect these elements around other stars, then perhaps we can detect this around other stars. So here we have a perfect example of organic material, intelligent life, liquid water, in the form of my cousin Hank, who is now like twice that big, which is amazing. But anyway, so this is kind of what I imagine as our motivation, is to find life eventually. But how does one actually go about detecting these sorts of molecules in protoplanetary disks? So one way to go about doing that is to actually use the information that remains from when our own solar system was a protoplanetary disk, and thank goodness, comets actually act as time capsules that have frozen the chemistry of when they formed in the disk. And from observing comets, astrochemists have been able to determine that when our solar system was a disk, ices were dominated by water. And if you were looking for nitrogen, you'd often find it in the form of ammonia. So the ammonia to water ratio becomes a useful metric for us to talk about here. And in the ice phase in the disk, we have determined that the ratio is about 1% ammonia to water. So more water than ammonia. Very interestingly, just this year, Mikhail Salinas and a team that includes our own Ilse Cleeves here at Harvard pulled off the very first gas detection of ammonia in a protoplanetary disk, this time not our own solar system, but in TW Hydra, which is a system about 50 parsecs or 180 light years away from us. And most interestingly, in the gas phase, we determined that the ammonia to water ratio is actually 7 to 84%, which is admittedly a large margin of error, but is still simply different than what we had seen in the ice prior to this. So this could definitely indicate that there's new chemistry happening here, perhaps misunderstood physics, generally something we don't understand. So ideally, what we would love to do is look at this spectral line of ammonia and basically break it open and see what's happening inside to cause this elevated ammonia to water ratio. Unfortunately, as you know, this is absolutely impossible to do with observational astronomy and a disk that is literally 180 light years away. Fortunately, we can do kind of the next best thing, which is to use computational modeling. And so what I've been doing this summer is developing and using a model that allows us to input physical and chemical conditions, run that over a theoretical lifetime, and output final molecules, or in other words, what we would expect to actually observe with our telescopes. And the key point here is that we can break open our computers, figuratively, and see exactly which reactions are happening when, where, and with what frequency. And that provides a really powerful tool for understanding exactly, precisely which interactions are occurring here. And so that has led to a whole bunch of plots, which I will now show you, looking at how the ammonia to water ratio and also abundances of various molecules evolve over the lifetime of a disk. So a couple points for these plots. I'll point out that they're all log-log, so keep in mind that the time between the first two plots here is about 100 years, while the time between the last two ticks is about 1 million years, so that can skew how you interpret these. And secondly, I'd like to point out that the lifetime of TW Hydra and a lot of the disks that are currently being studied is around 1 million years. So we want to be looking here at the end of the plot to see things that might align with what we'd expect to observe. So this first plot that I've shown you is actually the ammonia to water ratio in the ice over the lifetime of our model. And this is actually an encouraging thing to see, because if you plot the 1% line, there's about a 1 order of magnitude agreement here, which makes us think that, okay, comet data is saying 1%, our model is saying 1 to 10%, maybe our model's doing good things. And then next, I would like to point your attention to these shaded bars, which I have at the center. Those correspond to the 7 to 84% range from the detection of gas phase. And now I'll add what we have received, the information we've gotten from our model in the gas phase. Very interesting dynamic behavior, changing by almost 10 orders of magnitude this ratio over the lifetime of the disk. And a really key point here is that each one of these lines actually is looking at a different location in the disk. So while this new detection that we have is actually unresolved, thanks to the long wavelengths that we use for infrared astronomy, we don't have yet, until we get ALMA data, we don't have resolved data for the entire disk. We just know that for the entire disk, the ratio is elevated. But that doesn't mean that everywhere in the disk the ratio is elevated. And actually what our model is suggesting is that in many parts of the disk, the ratio is remaining low in the gas phase. And actually there just seems to be a certain portion where that ratio is high. But if we think about how averages work, this actually isn't a problem, because if you have one high value, that raises your average, and this could very well mean that a concentrated region of high ammonia to gas ratio could lead to an increased detection overall. So anyway, looking at this particular region in the disk, we see about a 5 or even greater order of magnitude increase in the ratio. So this has been what I've been focusing on most of the summer, is trying to understand what could be causing this increased ratio we don't understand. So one of the first steps I did was to look into how chemistry affects it. So if you give the disk at the very beginning all of its nitrogen in the form of molecular nitrogen, or N2, or all in the form of atomic nitrogen, or N, or in equal proportions, then you'll see here that this actually has an effect on the behavior of, this is the abundance of ammonia specifically, in the last few million years of the disk, on the order of about 1 order of magnitude difference for these different cases. However, every single one of these cases retains this really large, in this case 3 order of magnitude jump around the same time. So it doesn't seem that the chemistry has a role to play there as much. So we wanted to ask a different question. What is the physics doing? So another thing that we looked at was ionizing radiation, and how the X-rays and cosmic rays, which are ionization sources that can blast molecules apart and turn them into ions, is affecting the abundance of ammonia. And here we see very clearly that if you turn off X-rays, you no longer see this increase in the ammonia abundance, which means that ionization is having a huge role to play here. But this still isn't the whole answer. So if you really want to understand even more nitty-gritty what is happening to cause this increased ratio, you need to dig into exactly which reactions are happening. And that leads to a figure like this, which I will admit is very complex. You don't need to get all of it. What you need to get is that we have a starting location shown in green, here being atomic and molecular nitrogen, and an ending location shown in red, which is ammonia. And we want to understand how you can get from point A to point B. Which arrows or reactions are most important and what affects those. So for example, the arrows here that are shown in orange are strongly dependent on the X-ray flux. So as you can imagine, if you turn off X-rays, you lose those pathways, and it makes sense that you would see less ammonia, as we saw in the previous plot. But I like to think about this plot and this process as actually like a murder mystery. So we know that we have an increased ammonia to water ratio. So what could be the culprit for that? So there could be, if you're looking for clues, you can look for somebody who's showing positive clues that they might be the murderer. So they're angry, they're talking too much, they're really acting out, maybe they've murdered somebody recently. So if you look at if something has increased that produces ammonia, you have more of something that creates ammonia, that could be a positive clue. Additionally, you can look for negative clues. So if somebody hasn't come into work, if they're being really quiet, kind of suspicious, maybe they've murdered somebody recently. So if you see less of something that destroys ammonia, in this case ions, which are not coincidentally dependent on X-rays, then that could be a reason that you might have increased ammonia in the disk. So this is part of the story. I've spent a lot of time looking at each of these arrows or reactions and trying to understand which one might be the culprit. Unfortunately, we haven't come to an answer quite yet. Hopefully that will be coming soon. But there remains many more things to examine in these systems. So in addition to looking at chemistry and the flux of cosmic rays and X-rays, I hope to look into how ultraviolet radiation plays a role. Also, as you can see here at the top, carbon and oxygen have a huge role to play in the production of ammonia. So eventually, I'd like to examine how changing the abundances of those molecules might affect the ultimate ammonia to water ratio. And perhaps intuitively, but took me a while to get to, if you want to understand the ammonia to water ratio, you also need to understand water. So that is a long, complicated question that I have just begun to unpack. And thankfully, I'll be continuing this project for my senior thesis when I return to Yale in the fall. So I will have months and months to keep asking these questions and diving into this. So to summarize, this summer I have been investigating what seems to apparently be a discrepancy between the ammonia to water ratio in the ice and the gas or protoplanetary disks. And what we have found is that it doesn't necessarily have to be a discrepancy at all. In fact, our models have proven that you can have simultaneously regions where you have a high gas phase ammonia to water ratio and a low ice phase ammonia to water ratio in these systems. And the real question we're asking and will continue to ask is just how. So I would like to thank profusely Professor Johnson, my amazing mentors, Dr. Öberg and Dr. Cleeves. I love all of you in the Banneker and Institutes. And thank you to my fellowship at Yale, which is funding me. And most importantly, perhaps, my parents, who I wish could be here today, but who have been supporting me from the very beginning. But anyway, thank you very much. Thanks.
All right, what questions do we have from the audience?
So did you look, so looking at the discrepancies and stuff of that sort, do you think that did you look at the stellar evolution or how that may be affecting, how the protoplanetary disks are forming, or could you get any information of, because you say go back and study, our own solar system, can we go back and even study the star that's forming to be able to tell us some information about that?
Yeah, that's a wonderful question. Yeah, and actually, TW Hydra is a really great system for that question specifically, because it turns out that we're looking at the disk face on. So you see the disk that I have in the background here is actually not TW Hydra, that's HL Tau. But if you see a picture of TW Hydra, it's just a circle, and the star is right there staring us in the face. So we can get a lot of information about what's happening with the star, and there have actually been a lot of studies about that. I personally didn't look into that as much in my project, but in the future that's definitely something I want to keep in mind, to think about how these results agree with the measurements we have of the star itself.
Oh, question up here, in the back.
So I have a question about how you deal with the timing because, for instance, if you're looking at X-rays, you kind of expect stars that are X-ray bright to be more variable, let's say. So are your models like assuming that the flux from the star is always steady, or is there some variability in there?
Right. So for this particular model, we did assume a steady X-ray flux, but the best thing about computational models is that you can change that whenever you want to. So I know that actually Ilse is currently working on some data for IM loop, I believe, which has already seen some really obvious variation in the X-ray flux. So she's been using a model that does incorporate that. And it would be completely feasible for me to include that in the future if that seems to be something we are actually observing in TW Hydra. Yeah, thank you for that.
Another question from you? Yep.
Yes. So in the beginning you talked about adsorption, desorption, and some, I forgot the other one. Dissociation. And so in the graphs that you showed, did those played a role, right?
Yeah.
Okay, but
yeah, absolutely.
Right, so then I'm going to ask a question about that. Like, do you know like how much percent each of those play in?
Yes.
Discrepancies that
So there's a complex answer for that. All of those are always playing a role.
Okay.
So yes, that is. I kind of want to talk to you about that extra after because it goes for a while. But basically, if you see, particularly the ice curve that I showed you, if you see more adsorption, so more freezing out, then you would see an increase in that ice curve. And the same thing if you see a decrease in gas. That could be due to more adsorption, where you're losing gas phase and freezing things out onto the surface. But yeah, all of those things definitely play in. And that's exactly the processes that are kind of behind the curtain of what's happening in this model and in the systems in real life as well. Yeah.
Just out of curiosity, the logarithmic plots you have, what were the axes?
These?
The logarithmic ones.
Whoops. Oh, from the results. Okay, did I not say that? I'm sorry.
Okay, so time.
Yeah, always progressing in time over the course of, I believe I ran to 3 million years. So each of them is running 3 million years. Some of the early ones were the ratio of ammonia to water, and then the ionization and chemistry plots were actually looking at the abundance of ammonia exactly, specifically.
So, I see. So it's like smaller changes over large, very large.
Yeah. That's where the log part comes in. It makes everything a little non-intuitive.
So your models seem to be saying that you can have higher or lower abundances of ammonia in different parts of the disk. Do the regions that have lower abundances match where we might think that comets would be forming that we see have those low abundances?
So I can definitely say for the very first plot that I showed with this ice, so I'll just remind you that comets are our marker for ice in the disk, not gas. So the ice curve, yes, does seem to be agreeing with comets, and this was pulled from the cold midplane, which is also where we believe comets to form. So yes, I hope that answers your question.
All right. One last question here? Yeah.
Sure.
Because you mentioned that you had very, originally we thought it was 1%, but in reality it's like anywhere to 84%. It's very large. Has that always been the case, or does it follow this trend over time? Because it seems here that you've got the change basically going up to like somewhere closer to almost 100.
Right. So there are 2 points to that question. So the first is actually that the 1% and the 7 to 84% are two distinct measurements, and they're not actually describing the same thing. So 1% was in ice, and 7 to 84% is in gas. So even though the numbers are different, that doesn't mean that those two things can't both be true. And to answer the second part, yes, these are definitely changing over time. So the observations that we get from comets and from the new gas phase detection are from where the disk is right now, where we believe to be about 1 million years old. Though it seems to be, our models do seem to be suggesting that there was a lot of variation in those numbers over the lifetime of the disk. Yeah.
All right. Well, excellent job.
Thank you.
Thank you for sharing your research.
Yeah.